Okay, so in this video we're going to look at uh, two phenomena that occur when a ray ap approaches a material, and one is reflection and the other one is refraction. Let's start with specular reflection, and that occurs when there is reflection from a flat, smooth surface like a mirror, right? Then if that happens, if you have a flat, smooth surface, then this is called specular reflection. And so there is we have a simple law to describe what happened here, and that is called the law of reflection. And it states that if this is your incident light here, coming this way, and it gets reflected at this point, and this is your mirror, your reflected surface, which is smooth and flat. So you get this light coming in here, and this is a normal to the surface here, right? This is a normal line. So you can measure this angle theta I, the incident angle, right? The angle of incidence. And you can measure this angle theta R, the angle of reflection. And what you find experimentally, and this is the law of reflection, is that these two angles, the rays made with the normals, they are equal. So that's the law of reflection. Now, there is also diffuse reflection, and that happens when light is reflected from a material that is rough and is not flat. Okay, so you can see at every point here there is a normal. Here there is a normal, and there is a normal, and the law of reflection is being obeyed. But the surface is so rough that you're not going to get the rays being reflected all in the same direction. So diffuse reflection is very important because it's what allows us to define objects and to see objects actually. Uh, Now let's see what happens to to a mirror, and consider here we have a point P, and this point is a source of light, and then you have rays coming out of P and they get reflected, right? If you're looking at an image here, right? If you're here, then it's gonna look to you as if the light is coming from this point. This point P prime is called the virtual image. The distance of this S prime, this is called the image distance, or the distance of the virtual image. And this S is called the object distance. And what we can say for these flat mirrors, is that these two values are the same. S is equal to S prime. That is just a simple mathematical equation that we can use to describe the physics of plane mirrors. So, and then we can think about objects, right? So now we have this pine here, and we have lights. We have lights coming from both P and Q, and they come and get reflected here, right? So then it's gonna look, the light coming from P looks like if it's coming from P prime. The rays coming from Q, they look as if they were coming from Q prime, and the image you're gonna get here in your eye. So then this distance here is the image to the object, to the distance to the image. This is the distance to the object, and and this is how you basically see this image reflected on a mirror. The other important phenomena that happens when light crosses or approaches an interface or crosses material is refraction. Here we have a laser, and this is some glass, and what you see is that there is a ray that is reflected, okay, and this is the normal here, and this gets reflected, but there is one that gets transmitted. And what you see here is that the direction of this direction here changes. This ray that gets transmitted is not following the same direction as the incident ray. So this phenomenon is called refraction. And there is a law to explain the refraction. And basically, if this is your incident ray and this is your normal, then this is the angle of incidence. Then what's going to happen is the refracted ray, this one here, make this angle theta 2 with the normal again. And these two angles, theta 1 and theta 2, they are related by this equation. N1 is the index of refraction of this medium. N2 is the index of refractions of this medium here. And the sine, these are the two angles, and N1 sine theta is equal to N2 sine theta. This is Snell's law of refraction, and you can actually you can prove this law from electromagnetism, and those of you taking general physics 2 will do that next semester. We'll see how that can be done next semester. And but you can also check this law in the lab. You can do this experiment in the lab and prove that this is true, that your experiment uh, agrees with this equation. So if the direction is reversed, then what's going to happen is that, well, this angle, the equation is still obeyed, but now the theta 1, which is now the light is coming from medium 2 into medium 1, and theta 1 now still greater than theta 2. So there are indices of refraction for various mediums. Here, vacuum is 1, air is almost 1, and for most calculations, we just use 1 for air. Water is 1.33. Notice that they are all greater than 1. That means that the velocity of the light in that medium is smaller than c, the velocity of light in vacuum. And there is another important thing that happens when a ray is transmitted into a material with higher index of refractions. It bends towards the normal, like this case. Medium 1 could be air, medium 2 could be glass, so it bends towards the normal. When air is transmitted from, say, glass to air, then the light bends away from the normal. So here is a question: a laser beam passing from medium 1 to medium 2 is refracted as shown. Which one is true? N1 less than N2, N1 greater than N2, or there is no information? And the answer is, well, this guy is bending away from the normal, so N2 have to be less than N1. So to analyze refraction, we need to draw a ray diagram and draw a line normal to the boundary, and then show the ray bending in the correct direction, and then label angles of incidence and refraction, and then we use the Snell law. Another phenomenon that could happen is that if light is coming from a medium with a higher index of refraction, then there is a possible angle at which there's no light being transmitted. This is called total internal refraction. Here you have blue that is hidden, is traveling in glass here, and is being totally reflected. Okay, notice that it happens here because it's being reflected at a certain angle. It doesn't happen here, it just happens here. So that angle is given by this equation, and that happens when, well, when theta 1, when theta, this is your light here, so this light gets transmitted. So you see the lights, they get refracted away from the normal, and there is one here, there is a particular one that makes this theta 2 equal 90 degrees. When theta 2 equals 90 degrees, then you can write this equation and find theta critical. Theta critical is this angle here, and that is the angle that gives you the total internal reflection.